Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So let's continue our class today with the distributed computing using Julia. Okay, so what we will discuss is how do we create a Julia cluster. Okay, and then programming parallel tasks. Okay, then shared array and the summary at the end. Okay. We are focusing now. We have two type of programming models. We have the shared memory, okay, shared memory, okay, and then we have distributed memory. Okay, remember in shared memory we are normally using threads, okay, and in distributed memory we are using the processes. Okay, so what we have here, if you are using thread, we can share the memory. So we allocate some memory here, okay, and then the thread can access thread 1, thread 2, thread 3 can access the memory. So they can, if you are allocating matrix A here, then thread 1, thread 2, thread 3 can also read and write matrix A. Okay, different from shared memory, we have distributed memory. Okay, so you can have within a computer. Okay, so we have here process 1 has its own memory, process 2 has its own memory. Okay, so when you what you call allocate matrix A, it is different from the process 2 matrix A because it is not shared unless you are sharing explicitly, okay, using some message passing. Okay, using message passing. So you are passing the A from process 1 to process 2. So then process A, process 1, process 2 will have the same A. But again, this one also not shared, so that anything happens on this matrix A will not be reflected in matrix A here. You need to explicitly again synchronize all the what's called the matrix A if this is required. Okay, so this one can happen within a computer. So you have PC number 1 here. Okay, it can happen also in cluster computer. So in cluster computer, you can create another process. So let's say here the same name, process 1, but this is on PC number 2. Same name here, process 2, but this is on PC number 2. Okay, so you have memory here, you have memory here. So you're creating A in here and A in here. It's different from A of process 1 PC1 or A of process 2 PC1. Okay, so you need to explicitly send. So normally you have here a network in which you can send between cluster, okay, between the PC, from between processes. So from process 1 can send to process 2, from process 1 can send to process 1 on PC number 2, or process 2 on PC number 2 here. Okay, so again, it will be using the message passing. Okay, but Julia try to minimize the control, okay, so that you can use directly. Okay, so you can focus on the algorithm. Okay, so let's start with the Julia cluster. So how to use how to start Julia cluster? The easiest one is to use here Julia minus P4. So 4 here representing 4 process, 4 workers, or 4 slave. Okay, so when you create like this, you'll have 5 Julia process. If you are checking using your task manager or using your Htop in Linux, okay, so you can see that Julia creating 5 processes. One is the master, okay, master, and the other 4 is the workers or the slave. Okay, so the communication between Julia process is one-sided. So you are process 1 to process 2, you send the message here. There's a master process that accept user input and control all the other process, and also print the output is normally on the master. Okay, so the master will do the IO operation, reading the file. Then after that, in the memory, that it can send to the workers. Okay, then the workers can do some calculation. Okay, so you can use this one. Okay, or the other one you can use. See the prox method here. This is the built-in Julia function, so you don't need to add. So using distributed, okay, you can use using distributed here. Okay, then when you type prox, as I mentioned earlier, you have 4 workers or child process, okay, and 1 master, okay, master process. Okay, the master will do the IO and and so on, printing the output and getting the input. Okay, so you can use also the add_prox method. Add_prox n and is another slave, another workers that you want. So it behaves similar to -pn, but it is a pure Julia function. Okay, so for example, here's the process as one earlier. This is the master, and you have 4 workers, and then you add process number add 2 more process. Okay, then you have process worker number 6 and worker number 7. So altogether you have 7 process. Okay, so you have 7 process. Okay, and normally what we do is to run as many Julia process as the number of cores on that on the logical cores. Okay, because if you have like Intel or AMD, you have hyper threading, then you can have physical logical core is normally twice the physical core. Okay. Okay, so starting Julia process, the responsibility of a component called the cluster manager. Remember that when the term is distributed memory, okay, normally this one also equivalent to a cluster. Okay, equivalent to cluster. Okay, the simplest is local manager in which is built into base of Julia. Okay, so this one is only on local host. Okay, so you're creating, for example, if you have 8 cores, then you want to create the process 8 process. Okay, maybe 7 workers. Okay, so 1 process. So you can have add prox 7. Okay, because it will create the 8 process. Okay. So the other cluster manager built into Julia is the secure shell manager. So previously what we have local manager. Okay. Now secure shell manager is needed when you want to access other PC. So you have here PC number 1, for example, and you have here PC number 2. Okay, as your worker or the slave. Okay, so you want to be able to remote access PC number 2 from the master. Okay, so you want to be able to remote access PC number 3 from the PC number 1, the master. Okay, that remote access normally we use it the SSH. Okay, so there are what you call 2 requirements. The first requirement is ability to SSH from the master to all other nodes. So that's why you need to install a SSH server on the worker or on the slave, and then you can install SSH client on the on the master here, on the master node here. Okay. So, and the other requirement is the Julia binary must be available on the same location on each machine. So that's why it when you have multiple PC, it is easier if it is uniform. Okay, so you have using Ubuntu, for example, and it has the same directory to install Julia. For example, you have home user and Julia user, for example, and then you .julia. This is the bin that you have. Okay, so in that case, then when you do SSH with your user, user at some PC number 2 and so on, that it can run the same without specifying the directory. Okay. So how to use that one? Then you can have add prox, and then you can see this one, the PC number 1, for example, and this is PC number 2. Okay, so you can specify there. Okay. The other one is you can using the minus machine file option while starting Julia. So you type on your command prompt Julia minus machine file, and then you put the file here. Okay, the file will have host number 1, host number 2, host number 3, the list of hosts that you can work forming a cluster. Okay, so this is the SSH manager. Okay. Okay, so let's move on. So the master process connects to the worker of our SSH and start a Julia process on each worker node. Okay, so SSH can be passed using the SSH flag or keyword argument so that it will be automatic. You don't need to enter your password anymore because you have created a secure channel between the master and the worker. Okay, so SSH is only used to start the process. Subsequently, the communication occurs between the master and the workers of a plain TCP socket on ephemeral port that each worker listen to. So normally port 22 is used for communication. Okay. So the master does not listen on a port, however, all workers communicate with each other, and so any firewall policies must be set accordingly. So another requirement is you need to enable the firewall so that from remote, the SSH port, okay, so that it can communicate, okay, between workers. Okay, another one, the other popular one, if you have a multiple cluster, okay, cluster like this, you have PC number 1, 2, 3, 4, 5, and so on. Okay, 100, for example, 100 cluster. You can use cluster managers package in which you can find many different cluster, popular different cluster type. You can see Slum, SGE, PBS, so you can see, you can find out what is this, but the particular one is Slum is the most popular because normally it is installed on high performance computing installation here. Okay, so you need to do salloc, slum alloc minus how many nodes, how many CPU per task, and then pass it to sbatch Julia sbatch. Okay, slum batch. Okay, and Julia's slum batch look like this. Okay, and to start the Julia module for how long here? Okay, 15 minutes. Okay. Okay, then let's move on. And the start script provided by the user, start Julia, is responsible for starting the Julia worker process on the Slum allocated node using the cluster managers package. Okay, then you can use add procs functions. Okay, with in turn call Slum srun. So you need to install first the Slum package in Ubuntu and so on. Okay, then after that you can run here srun. Okay, Slum manager, you can see here. This is specifically using the Slum manager for how long. Okay. Okay, so yeah, for more information we can refer to here. Okay, clustermanager.jl. There's the documentation and example of code. Okay, now let's see how do we communicate between Julia process. Okay, so as we mentioned earlier, you can have on different PC. So, but this is process number 1. Let's say to make it simple, process 3 is on PC number 2, process 4 so PC number 2. So this is on PC number 1, PC number 2. Okay, so how do you do communication between the process? You can move the code. Okay, you can move the code. Okay, you can copy the code. And the other one is you can do remote reference. Okay, so you can put here matrix A, then can be accessed by the other worker, for example, or you can copy what you need to do with the matrix. Okay, you can copy the function. Okay, that one is the remote call function. Okay, so remote call, we request to execute a function on a particular node, whether it is built-in function or you create your own function. But remember, if you create your own function, then you need to be copied to other process, okay, to other computers. Okay, so and when you do that one, such a call is asynchronous. It will not wait. Okay, asynchronous, it will run on its own. So remote call finish immediately, returning the feature object, okay, which is a reference to its result. Then the argument to remote call is the function name itself, the process number to execute the functions, or on which worker. So you want to execute on P1, P2, P3, P4, so you need to define. And then the arguments to that function. So let's see the example. For example, you want to have square root here. So this is square root function on which process. Okay, this is process number 2. Okay, and what is the parameter? So we are doing actually like this. Okay, the result of course 2.0. Okay, so you are remote call that one. Okay, then wait will make sure that it's synchronous. Wait the A to finish calculation, to do the calculation, and fetch A, you have this one. But the simple use is you can use remote call fetch, in which you do all these things, wait and then fetch. Okay, so remote call fetch, the same thing, square root function, and this is on process number 2, and this is 4. Okay, 2. Okay, so you can do task parallelism. Okay, you can do task parallelism. What I mean here, if you want to try various method, for example, square root 2 and then what else? For example, absolute, comma, do on worker number 1 4.0. Okay, you can try also other things. Summation, not summation, maybe sinusoid or something. Okay, on worker number 3, 4.0, and so on. Okay, so this will create a possibility of task parallelism. Okay, different workers can do different things. Okay. Okay, now let's move on programming parallel tasks. So we have the useful macro, which is the everywhere, as the name implies, everywhere will do something here. Okay, so you need to load to add the distribution. It's not distributed. Distributed is built in, so you can use directly, but this is distribution. So you need to add the distribution, then using distribution, and then everywhere using distribution means that on process number one, Julia process number one, Julia process number two, it used the distribution, it uses also distribution. Okay, so everywhere print random normal here. Okay, so you can see here from worker 3, produce some result, worker 2, worker 5, worker 4, produce some result. How about worker 1? Worker 1 is default as master, the one that printed this one. Okay, so this one is only 2, 3, 4. Remember that at the beginning we only add 4. Okay, add prox 4 here. Okay, so in fact it print is on here. Okay, print is on random number here. Okay, for process number 1. Okay, which is the master process. Okay, so yeah, so we need to install the package in our environment in all nodes. So you need to add here in all. If you have PC number 1, of course, this one is okay. You can add here, but on PC number 2, you need to add first also here. Okay, you need to add the Julia, run Julia and add the distribution, and then after that you can do remote call to that to that PC. Okay. Okay, so another macro which is simpler is spawn. Okay, spawn is you create in multiple worker. Okay, so to run a function in a remote process without having to specify the remote node or having to work through ambiguous syntax. Okay, so you don't need to specify the remote nodes, like something like remote call. Okay, but you don't need to specify the function. Remember that we do remote call, do square root, which process, and then the parameters, right? So here we can do spawn, just add some spawn here. You can see there's how intuitive the Julia is. So just add some spawn here, random normal 5,5 and square it. Okay, then fetch a, then you have this one. Okay, so so this one will actually create a closure around the code. So this means that any variable declared on the current node will be copied over to the remote node. Okay, so let's see on the next code, the random array is created on the remote node itself. Okay, so what it see here is do two things actually. So you have process 1, do some a equal to random and 5,5. Then it send process A to process number 2 to do the square, Okay, then send back here. Okay, so you have two process there. Okay, so you can see here b random 5,5. Okay, in here you do this one. Okay, random array is created on the current node and copied to the remote node. Okay, so this is spawn b square root. Okay, fetch a, so you get the result here. Okay, so we can see how expensive is that. So let's see the first process. Like I mentioned, this is copied. Okay, because you can see this is on the current node and then spawn to other node. Okay, so, then fetch the result 2.2 seconds. If you spawn on the remote node and then square it, okay, with the same size here, 1000, you can see 0.64. So this is faster. So because you can see that when designing distributed system or parallel program, it is crucial to consider the impact of data transfer between the nodes. If you remember the M-dash laws, okay, M-dash law. Okay, so speed up is equal to 1 over alpha plus 1 minus alpha divided by n, number of workers. Okay, so the alpha is the serial portion here. Okay, serial portion. So what's constitute alpha? IO operation. Okay, because it cannot make it in parallel. Okay, and IO is expensive. The other one is communication, another form of IO operation actually. So this is also expensive. So when alpha is bigger, so you have more IO, you have more communication, then speed up will be lower. Okay, so inversely proportional to the serial portion. Okay, so the speed up is inversely proportional to serial portion. So that's why you want to minimize as much as possible the communication and the IO. Okay, so an extension to the spawn macro is the spawn add. So the name implies here, add means you are specify on which node. Okay, it specify which worker node should run the job. So in the following code, we actually ran in worker number 2, but execute the addition in worker number 3. Okay, so random in worker number 2, but addition in worker number 3. So how we do that one? So our remote call random. So this is remote call. Okay, 2,2. This is on process 2. This is random 2,2, the parameters. And here as spawn at 3,1. Okay, add and fetch R. Okay, fetch R here. Okay. So when you fetch S here, the fetch can be used to result in any worker, not restricted to the master. Okay, so you can, this is S is spawn at the worker. Okay, so you can fetch the result. Okay, this is the fetch R. Okay, this is also fetch S here. Okay. Okay, so another what you call a method to use is the parallel for. So we just add something like this. See the difference here. This serial add for I. This is just put distributed. Okay, and you have plus here. You put plus in here. Okay, and this is for loop. Okay, so you do parallel loop here. Okay, parallel add. Okay, we can see the time. So serial add 4.5 millisecond. Parallel add is 2.7 milliseconds. So you can see the speed up there. Okay, another one we can use the parallel for loop we saw previously can perform on a reduction that is in that code and works for even if the computation is lightweight. Okay, there's no only slight computation. Okay, but the iteration is heavyweight, mean you do a lot of computation and there's no reduction to be done, summation and so on. Okay, or find the minimum, find the maximum. That's the reduction. The parallel map construct is useful. Okay, so means that you want to do, you don't have a one number. Okay, the one output number here, but you want to process part by part here. Okay, so this one go to process number 2, number 3, number 4, and number 5. Okay, so you want to work on this one and then produce the same size. Okay, so in that case, then you can use parallel map here. Okay, so let's see here in this code, we create a 10 large matrix and perform a singular value decomposition. So SVD is computationally expensive or heavyweight, you can see here. So it do a lot of computation to find the matrix there, the output matrix. Okay, so you can see here everywhere using linear algebra. Okay, so even everywhere the loading of the library, you need to load everywhere here. Okay, this is after the add procs. Okay, and this benchmark time map SVD, x. So this is 30 millisecond. When you do the parallel, just see the difference. Just add some p here. Parallel map SVD, x. So this is 19 millisecond. Okay, so you can see the speed up there. Okay, just change M to P, but not all. Okay, I mean, you can do, if you have some computation, you can try just do parallel map. Okay, and see whether you can what you call it's it's allowed to run in parallel. Okay, and see the benefit of just changing the minimum of your code, but you can see the benefit here, the speed up benefit. Okay. Okay, now let's see the difference between Pmap and distributed. They seem similar except the built-in ability to reduce in distributed. So you have the built-in ability, so you don't need to use here, for example. But the crucial difference is in how they distribute and allocate work to the nodes. Okay. So the Pmap function takes the list and pass each element of the list one at a time to each worker node. So as each node return the result, the next element is sent out to it. Okay. The distributed macro, however, divide up the list into a number of blocks corresponding to the number of worker node available, so directly distributed. So each worker is then sent the whole block up front, giving it all the elements required to operate in one message at the start. Okay. So the Pmap function is useful when the operation on a single element is reasonably time consuming and the number of elements is relatively small. Okay, because otherwise you'll have so many communication. Okay, communication time. Okay, remember the communication will add up to the cellular portion. Okay, of your parallel program. Okay, so this amount of code is better when each operation is very quick and every element takes approximately the same time to be processed. Okay. Now let's see the example of distributed Monte Carlo. Here we calculated the value of pi using the Monte Carlo simulation. So you copy the function here everywhere function dot in circle. So this function is copied to all the worker number 2, 3, 4, 5. Now has the copy of the function dot in circle. Okay, then this is the pi distributed. Okay, you can see here the Pmap. Okay, and then your see this is the running the function. Okay, for this is the parameters. Okay, this is the parameters. Okay, then you divide that one, you have the result here. Okay, and this is the serials, just 4 times that in circle. This one using this function divided by n. So here you are sharing the code. Okay, here you are sharing the data. You distribute the data. Okay, not share, but distribute the data. Okay, this one share the whole code. Okay, so that on each worker I can run this dot in circle. Okay, remember that this function, when you don't copy that, let's say that in circle is one function here. So if you don't do everywhere, it's only available on process number 1. Okay, F1, but on process number 2 it doesn't have F. Okay, it does not have F. Okay, so when you run it will produce some error. Okay, so let's see the difference. Pi distributed 107 millisecond and pi serial is almost 2 times. Okay, slower. Okay, another one is distributed arrays. Package is provide an implementation of partition multi-dimensional arrays. So they can be used to store data across multiple machines when the data is large enough that it does not fit in the memory of one machine. So for example, you have PC number 1 have 8 GB and PC number 2 also have 8 GB, and you want to create an array 16 GB. Okay, so you cannot use if you don't use the distributed array. So but you can, if you use distributed array, then you can split. Okay, so 8 GB on PC number 1 and another 8 GB on PC number 2. Okay, so as the name implies, this one is distributed. Okay, so the copy A here is not the same like this one, because this one have the half portion of A, this one also have the half portion of the A. Okay, and then from there also we can distribute the computation. Okay, so this is a good thing for data parallelism. Okay, so distribute the data and distribute the computation. Okay, so but this is not non-built-in function module, so you need to add. Okay, so using this one, you need to see everywhere here. This is distributed zeros, so you can see 12 12. So then you can see this one will be distributed. Okay, 12 5 mean we have how many? 4 process, so this 12 5 will be 4, so each one will have 3 by 3. Okay, 3 by 3, 3 by 3, 3 by 3, 3 by 3, so altogether will be 12 12. Okay, so existing array can be distributed as follows. So x random 10, or then after that you can if you have existing array that you have random, for example, not zeros, you can distribute the x is distribute. Just see here, distribute x, that it will be distributed, okay, across so many workers, okay, that you do earlier. Okay. Okay, so let's see. Sometimes the creation of the array itself must be distributed. So this one is not distributed. We create the array, then after that distributed. What if we just distribute the this one split, and the creation of random is split in the worker itself? Okay, so we can use the D array constructor. Okay, so for example here, everywhere function per I. So you size I-1 size here and fill my ID with D. Okay, or you can use this function also distributed array with the par. Okay, this is a function par. Copy the function 800 800, so it will fill with the ID. Okay, it will fill with the ID. Okay, so then for each distributed array, D here, this is D from where yeah, D from here, I think. So the index is the you can see this how it's split. Okay, and the local part you can see spawn at process number 2, local part D. Okay, means that if this is distributed, okay, this is to process number 2, process number worker number 3, worker number 4, worker number 5. So this command will have if you have the D array, the big D array, so it will work on this part only. Okay, so this is the local part for worker number 2. Okay, then fetch, it will print in the master. Okay, fetch from the master and you see the result here. Okay, so algorithm on distributed array must therefore be written to operate on local part as far as possible. So to make it so not to interact each other, so that you can you will minimize the communication. Okay, so you will minimize the alpha. Okay, so let's see here, we sum the local part of the distributed array on each node and then add the result together in the master node. So what you can see here, sum here, sum number 2, sum number 3, sum number 4, sum number 5 here. Okay, at the end, sum equal to sum number 2 plus sum number 3 plus sum number 4 plus sum number 5. Okay, at the end you add this one, but you add here first the local part. Okay, so this is so it will be faster, around 4 times faster. Okay, if you have 4 cores or 4 logic core, it will be 4 times faster. Okay, almost 4 times faster. Okay, the last one is the shared array. Okay, so previously we have distributed array, the array 2, 3, 4, 5. Now shared array, so the array is shared. So 2, 3, 4, 5 can read this one now. Okay, can read all the arrays. Okay, so the distributed array are a fully generic solution that scales across many network hosts that cannot fit in memory on single machine. Okay, so you have 8 gigabyte, 8 gigabyte, 8 gigabyte, 8 gigabyte. So you can have a 64 gigabyte. Okay, the maximum size of the matrix A. Okay. However, in many circumstances, we want to have something like thread programming. Okay, so it's something like thread. Okay, but we can use the shared array here. Okay, so we want multiple Julia process, not multiple Julia thread, but multiple Julia process to improve throughput by fully utilizing all cores in machine. So what they do, created by mapping the same region in memory to different process. So that's why this is shared. Okay, so process number 3, 4, 5 now can have the access to the matrix A. Okay, can have the matrix A, and process itself is different memory location, right? So different memory location. So you create some part that can share, that is shared between all the workers. Okay, so you use the shared array modules. Okay, you need to add, is already there using shared array. So you allocate here as equal to shared array, type of floating point 100, 105. Okay, and PID is 2, 3, 4, 5. Okay, so it means that it can be accessed by process 2, 3, 4, 5. Okay, so once a shared array is created, it is then accessible in full, not in part, in full. Okay, 100 by 100 to all specified workers. This one. Okay, on the same. This is on the same machine. Remember that we don't use now distributed. Okay, so PC number 1, PC number 2. So this is only on the same machine. Okay, so S here still different with the S here, even if you are using the shared array. Okay, because this one belong to the different machine. So if you are on the same machine, then this one accessible fully by all the workers. Okay. Okay, so let's see here. In here, we are using the Pmap. This is the shared array, and update with the my ID kind ID for each index S. Okay, so yeah, so you allocate here. This is 2, 3, 3, and so on. So you have 2, 3. So it will be filled by 2, 3, 4, or 5. Okay. So when the data is small enough to fit in the memory of one machine, but large enough to require multiple cores to process, shared array are particularly useful. Okay, not only that they are high performance in this situation, but it's also much easier to write code for them. So you can see here, just write something like this, and it can distribute the processing. Okay, not the what you call the calculation will be distributed. Okay. Okay, so the last one here on parallel prefix sum with shared array. So how we do the prefix sum? When we now distributed here sum, and then after that you add all these things. Okay, so how we do prefix shared here. Okay, when you put here means that the input become the output. So you update the input. So something like passing the pointer in C. Okay, so yeah, so you sing distributed, okay, and then sing again distributed, okay, and after that you put the inbound, okay, sync, or put the sync because you want to synchronize the result, okay, before you move on to the next one. Okay, distributed, you distributed the for loop here, and inbound because you are sure that there is no buffer overflow. Okay, so this for jk minus k, and this is k minus 1 minus 1 1. Okay, and this is a summation there. Okay, at the end you have the full y there. Okay, the output. Okay, so we have discussed the Julia cluster. Okay, how to start Julia cluster. Okay, and we have discussed the parallel task. Okay, you can use distributed array, you can use everywhere, you can use spawn macro, spawn add, okay, a remote call, and so on. And we have also shared array at the end. Okay, so thank you. See you again, inshallah. Assalamualaikum warahmatullahi wabarakatuh.